Hello people, I'm back, and this time with an informative video. I think this is going to be really good for you. I know it's been a long while since I've made a video last time, but I think this information, this one is going to make up for it in a big way.
YouTube.com/simracecheck.
So, if you are new into sim racing, and if you are anything like I was in when I started sim racing and got to a level where I just got control of the car and wasn't crashing all the time anymore, I was always thinking, how the H do these guys pull all this power out of the cars? It seems even if we're driving the same car, some guys just accelerate away. How do they do it? Well, much of the secret comes from shifting gears at the exact right moment, and some people just have a knack for it, and other people like me have to figure out ways how to calculate this, when the right time to shift the gear is. And now I'm going to show you this secret of calculating when it's the right time to shift gears, and you're going to get an actual scientific way of analyzing this. So what you need is a flat track. I've just loaded up Sebring here in my favorite sim, GTR2, but you can use this method in any sim that supports Motec data and has the speed of the car, your longitudinal Gs, and your RPMs of the engine in the Motec data output. If you have that, you can calculate this. So that would be iRacing, R factor 2, all the sims that support Motec data. So, way to do this is get into your car, put the rev limiter at the absolute maximum level, and then adjust your first gear to be extremely long, like at least above 200 kilometers per hour, like this. Second gear away, and then put first gear all the way up here. Now we are actually ready to test. Now you just have a basic setup that drives okay, and then do this. Now, go onto the track and start calculating data. And this is the part when I realized I had my microphone turned down way too low and my game turned up way too high, so you couldn't actually hear what I was saying. But you need to find a flat piece of the track where you can do a full acceleration in first gear. So I'm in open practice here. I can run the opposite direction, so I'm going to do that. And then I'm going to stop completely. I'm going to select first gear, and then I'm going to have the car rolling. And as soon as I can, without having any clutch slip, because I'm using automatic clutch here, but as soon as I can, I apply full throttle and then let the car rev all the way up, gaining speed all the way up till it hits the engine RPM limiter. So just letting the car accelerate until it hits the RPM limiter. Pressing escape, going back. So what I did was just let the car accelerate at maximum throttle for the for as long time as it takes until I get up to the RPM limit. So then I get some interesting Motec data. And the Motec data, I'm going to turn off some of the things that I haven't explained yet here. Like so. We're going to move this out of the way. What we've got here is a graph of the engine RPM. So this is idle RPMs here at 1825. And this is from before. I've done accelerations like this before and tests like this before. So it starts here accelerating up, gaining RPMs, gaining RPMs, gaining RPMs, hitting the rev limiter and flattening out. Equally, I've got over here the same kind of data, accelerating, hitting the limiter, flatten out, and then I just used the brakes or made ready for another test again. And down at the bottom here, I have the speed. So you can see here gaining speed as it's gaining RPMs. This is much the same. Speed to speed and end. Same over here in the test before. Gaining speed, gaining RPMs all the way up to 10,900. Stop, no more gain RPMs, no more gaining speed. Right. We need to now make a calculation that will tell us what at what RPMs is the maximum acceleration of the car. So actually a pure acceleration would be just using the cling. A pure acceleration would be just using the longitudinal G's, and we can try here and just take the maths here. I've got only one math channel here, and I'm going to completely ruin this now, but we're going to rebuild it, and I'm going to take just the longitudinal G's. So if we do that, the graph will look like this up top here. You can see how this has high longitudinal G's here in the beginning, because in the beginning the acceleration is the greatest, because here it's easier to pull the car along until the wind resistance hits the car, and then the acceleration, as we get up in the RPMs, actually the acceleration is decreasing here, and it gets smaller and smaller and smaller until at the top here we don't have no acceleration anymore, because we reached peak RPM and the rev limiter. So this is no good, because if we went from these data, we will see here that in the middle here it's about the highest. I think about here we would have this telling us that we had a peak power at 6,250 RPM, and I know for a fact that's not right. So we need to figure out a calculus here that gives us a much more a better result. So we know that the energy of an object is the mass of the object times the speed of the object, and we need to figure out how much energy we're putting into this thing. And since the mass of this object is a constant, we don't need to put that into the equation. We need something that will tell us how much the car is accelerating instead, and that's where we have the force, the longitudinal force. So let's try and find the product, multiply the acceleration by the speed of the car, and it's called corrected speed, and it's here it's alphabetically sorted, so it's corrected speed right there. So we have force longitudinal in G's multiplied by the corrected speed of the vehicle in kilometers per hour. And now our graph looks something like this. And you can see now that the peak of this would be right over here somewhere, and this tells us 9,885 RPMs. And we can go over here and take the second one. I think the peak is somewhere around there, but this is guesswork at the moment, and it says 9,580 RPMs. So this is not really good. We need this smoothed out. So what we can do is use tools in Motec, use a smooth function that it's got in here, and we can say over how many samples this should smooth it. Now this is at 10 Hertz, so it has 10 measurements per second, so we want to smooth that out onto data for an entire second. We can put in 0.10 in here, so it's smooth, parenthesis start, all this thing in here, and then parenthesis end. And then we get data that is smooth like this. So all the jagged edges are now gone, and it's much easier to find where the peak is here. So peak here now tells us it's about 9,280, and peak over here might be somewhere around the same. It's 9,800 something. But this is not taking into considerations the RPMs of the engine. And we know that the power output of the car is a function of the revolutions per minute times the torque of the engine. And since that's what we're trying to find out, we need to only calculate with the RPMs here. And since that is a product of those, this should also be multiplied in here. So we multiply that by the engine RPM. And now we have the complete function. We have longitudinal, g-force longitudinal, which is a measurement of the actual acceleration amount, and we have the corrected speed of the car, which is an expression for the energy of the car, and we have the engine RPM, which here accounts for the energy output of the engine. So now let's see what we have, and you can see immediately here that the peak of this has moved a little bit further out here, so we're now at just about 10,000, which I know for a fact is on this car the RPMs where it has the maximum power output. So this first measurement here is completely correct, and we can go up here and look. This is a little bit more hard to measure, but since there's a peak here and a peak here, I guess in the middle of those two, and again hit 10,000 RPM. So for this car, I would, from these two tests, guess the maximum power output to be at 10,000 RPM. And I can also use this graph to show how I should keep it, or which rev range I should keep in to achieve maximum acceleration. So I should keep this car between around 8,800 RPM to, you can read the RPMs down here, to about 10,600 RPM. If I stay in that range, I will have good power. Let's see from another car here. This is a Corvette C6R that I did previously the same test on, and we can see here I've got a test result right here, and let's find peak here, and it reads 5,730 RPM, and I know for a fact from reading the files that this has maximum power output at 5,750. So at the moment we're calculating with less than 1% of variation from the actual peak power of the car at that specific RPM. Then comes the problem: how do I in-game keep as close to these RPMs as possible? And into play here comes a little program that I made. This supports GTR, Evolution, Race, GTR2, R-Factor, basically iRacing, basically any of the most popular sim racing sims at the moment. Now, I was in the Dome before, so we measured that from 8,800 to 10,600, and I put this at start RPM, I put at 8,800, and I put the shift RPMs at 10,500. Now let's go into the car and see what effect this actually has. Now you can look here at the rev counter as I started pressing the throttle. So using this tool, I will always know when I'm in the optimal power band of this particular engine. So it's a very great tool to use this shift light program to have you stay inside the optimal power band and never again have this feeling that the guys you're driving with has much more power than you have, or that they're cheating or something. They just know what rev to shift at. And now with this calculus in Motec, and perhaps even using my shift light program, you will know when to shift to get the maximum power out of your sim racing car. So have fun with this in your racing, and I hope you have lots of victories and great racing, because you now know at what RPMs to shift at.
YouTube.com/SimRaceTech